gambling, man, especially when it's athletes and
Okay. So we are talking about spectroscopy, which you just took a quiz, you Randy, which is the interaction between what and what? What's spectroscopy? The interaction between, say it louder.
light and matter.
Light and matter, right? So.
There wasn't a back to that quiz, was there?
No.
Oh, I think maybe.
From the other quiz.
Oh yeah, the one before. One before.
I was like, what the hell?
There's the one before. Yeah.
Dude, I'm bad about that.
But it should be in your brain. So we need to set up a machine that can help us measure the interaction between light and matter, right? And something that can transduce the signal of that interaction into an electrical signal that we can, plot out and that sort of thing. So here it is, in a general sort of way. So all of these spectroscopic instruments, Anna, need to have a light source. Right? I'll have to have a light source. And we'll talk about a bunch of them. Right? And all the little arrows, John, coming from it here, probably trying to indicate what? Yeah, a bunch of different wavelengths. Exactly. Right? Because he's right. Every color corresponds to a different wavelength, right? So a whole bunch of different wavelengths coming from the light source. Okay. Then it hits a box, Pablo, and then all you do is you see one arrow coming out there. Now what's going on? What changed? What changed? Right? What is that? Yeah, what is the box doing? Selecting a wavelength. Now you can say color, but what if you're not doing visible spectroscopy? So it's best to say wavelength, right? A wavelength selector. Exactly. You have a wavelength selector.
I like this one.
We'll have another name for it, though. It starts with an M, Emily. Mono. There it is. How do you say it? Mono? No, not monochromatic. Monochromator. That wasn't in the reading? Monochromator, exactly. Monochromator. Okay. Then you have another box, right? And then look at both sides of the box there. And then it ends up somewhere. Robert, how about one of these other two boxes?
It's making my arrow smaller. I like that. I assume there's a detector somewhere.
Yeah, where would the detector be?
At the end.
At the end. You got the easy one, the detector.
Justice.
So Sandy, what would you explain what's going on in the middle? Remember, spectroscopy is the interaction between light and matter. Well, where's the matter, right?
It does not matter.
Right? You have to have it somewhere. So you might call it a cuvette. You might call it a sample holder, right? Whatever the case is. Probably sample holder might be the best, or the sample, right? Or sample holder, however you want to talk about it. So what's the meaning with the arrows doing what they're doing there, Kathleen? What do you think's going on there? Sample absorbing. The light is getting, there's an A, to use their absorb. Well, the sample's doing the absorbing, right? But if light gets less and less intense, what's the word for that? Starts with an A. Attenuated. That's the word that they like using, right? The light is getting attenuated. right? Or absorbed by the sample. That's right. Okay. Attenuated? Three T's.
Yeah.
Okay, so let's take a little closer look at the light sources. We have continuous or discontinuous. Adriana, what's going on there? What do you think that might mean? A continuous light source, a discontinuous light source. Yeah, yeah, but so you gotta leave it on, obviously. All they're talking about is the
light source. Is that why like the UV vis clicks on and crap like
Oh, that's something else. We'll talk about that. But it is, in a sense, why the UV vis is making all that noise, because the light source is continuous. It's kind of like this. See, it has all these wavelengths, right? And all that clicking and stuff you're hearing in the UV vis is for this wavelength selector to select a particular wavelength. There's a lot of rotating gears and all that. We'll talk about the monochromator. But this is an example of a continuous light source. It's just a big smear, Roy G. Biv, right? If I erased all of them but the purple, just one wavelength coming out, that would be a discontinuous light source. If I erased, I don't know, maybe all of them but the purple and the red, then it would be what they want you to think of is, let's say this is intensity and wavelength. If you made a little plot of what was actually coming out of the lamp output or the light source output, and if it's a big blob, right, continuous, versus that. Could that even happen? Yeah, well, it has to, because there's a word for it, right? Discontinuous. So single wavelengths getting kicked out of a light source would be an example of that. Is there one? There's an example of a light source that would do that. Here's some hints. Want to jump to discharge lamp? A discharge lamp. Here's my discharge lamp. But it needs a lamp in it. So what happens if you take, what gas is this? Deuterium gas. Let's make one that makes more sense. Air. Right?
Air.
Air. Very low pressure, though, but there's air in here. And you apply a huge voltage across it. What happens? Right? Now, what's odd is that, why would you apply huge voltage? That's a huge plus, huge minus, right? Why would air even care? Is air polar? Right? You're getting there, right? So what there is in here, there's also, they have a little bit of argon and things in here to make this work even more efficiently. But how did van der Waals forces work? Dispersion forces work? Do you remember? Because you take a molecule like oxygen, right? Is oxygen polar? No, it's impossible, right? But yet I can grab a tube that says oxygen on it. Or here's nitrogen. I can grab a tube that says nitrogen on it. Nitrogen's not polar. What's going to make it move to one guy or the other? collisions, right? It's instantaneous dipoles. Once there's little tiny partial positive, and then the thing starts shooting towards the negative side, right? And once you get these guys moving really fast, collide into each other really hard, they get the E word, excited, they emit their light, right? So okay, let's turn it on. Does that look like a continuous or discontinuous light source? I don't know. I mean, how can you tell? You need something that's going to spread out the light, right? Like, for example, let's blow things up. If you did the flashlight first. All right. Let's see. Get this guy then. There he is. Okay. Continuous or discontinuous? Continuous. You should know this because what's the name of the dude? Roy G. Biv. Right? They're all there. A smear. Right? Right? They're all there. And it's a smear. You don't just see red. You see them all. Right? But it stops, obviously, after the red and violet, but it's continuous. Okay. So in order to see it, you had to use one of these things. What's this thing? Grating. Okay. Now you can hold it up here and try to do the thing, or you grab one of these guys. I should have had you grab one when you took the quiz.
Plastic baggies.
Okay. Now you remember using these? I think I had pulled these out in general chemistry or something maybe. All right. So the trick to doing this is to make this guy black. I don't know if I can make him black or not.
Yeah, I was like, this is open?
Okay, well, that helps. Okay. So yeah, I gotta remember how to do this too. Yeah. All right, I remember now. So you see the little slit on the. Now you gotta hold the other way. Hold this way.
Yeah.
All right. So bat in towards the light, and you see the little slit. You gotta get the lamp lined up with that little slit. Okay. You see the lamp lined up that little slit.
I see orange on like the far left.
Okay. Now you have to get the line lined up with a little slit, and then try to look way into the far corner of this guy. Yeah, be careful. But look closely at Roy G. Biv.
It's split apart.
They're split apart. There's divisions. There's actual lines, right? Well, let's get one that might be a little easier. Let's try mercury, right? Because you might still think Roy G. Biv, right? Where it's not. It was broken. There's only certain reds, certain greens with the nitrogen. How hot is this guy? Hotter than hots. Thank you. All right. Try mercury. Hopefully you won't see so much Roy G. Biv now.
She's like, how do you miss it? It makes so much sense.
Oh yeah, this one behaves a lot better, right? All I see is like a purple line, a green line, an orange, and way over there a dark blue kind of.
I don't see that. You have to look way to the right.
Yeah. Or way to the left, either one. Okay. So a discharge lamp is an example of a what type of light source? Discontinuous, definitely. All right.
What is that? A discharge lamp?
That's a discharge lamp. Okay. Laser.
Can we look into into a laser next?
Ooh.
Yeah, you can look into a laser next. All right. The next trick, but you got to use the grading, right? What's your guess? Discontinuous or continuous? Yeah, it's just. Now there's orders of diffraction, so you're seeing the same thing. If you remember looking through the little black doohickey, you saw the lamp in the middle, and then you saw the lines on this side, and you saw lines on that side.
Yeah.
So how if I change colors?
Wrong way.
Does it matter? All right.
Yeah. Okay.
Now, which one?
Are you in the same spot again? 'Cause it looks like there were more dots.
Yeah.
It's just order. I probably got closer or something. How about which one looks more nauseating? As a
Green one like hurts here.
look at that green one, doesn't it?
I'm looking at the
See what we've been
reflection,
saying?
they look the same.
Right?
Holy shit. Okay.
See what we've been saying? How which color is much more your eye is much more sensitive to?
I'm green.
That lime green.
I can't look at
So when I'm in a really bad mood,
you. Damaging my
I'm using this guy as my laser pointer when I'm pissed off at you guys, right? When these first came out, I thought, ooh, so cool. So I used this all hour in class, and it was horrible, right? I don't know why I kept using it. But look at that. Isn't that bright?
Yeah, it's really bright.
But if you wanna have a lot of fun, get one of these and then go camping. No, not right? In the trees, squirrels go nuts. Right?
So your drunk neighbors, I think it's cars.
Okay. It's easier than building a campfire. Okay.
Well, you just light the squirrels in?
Like green laser pointer? I don't think so. Okay. A monochromator, how does it work? Selects one thing, exactly. That's the whole point of this. Laser is discontinuous. Pretty much that's only kicking out one wavelength.
Yeah.
And if you read the small print, it actually even tells you what wavelength it is that they kick out. Okay.
And what's the
Also,
definition
it's by the warning.
between discontinuous?
Discontinuous is just, I think the definition is,
Scroll up to the little plot.
to me, this is the best definition right here.
That's discontinuous. Remember?
That if you take a look at what's actually coming out of the light source, if it's only certain wavelengths, it's discontinuous.
But if it's under all wavelengths, it's continuous?
But if you get it, even if you just take a little smear in here, and there's a certain region where all the wavelengths are there, that's continuous. It can be pretty dang narrow, but as long as all the wavelengths are there between two different wavelengths, that would be continuous in that range. So I think this is the best way to describe continuous and discontinuous, is that plot of intensity versus wavelength of the lamp output. Now to get that plot, I would have to shoot the light through the whole thing through a monochromator, right? And then have the little detector over here. If I was going to get that plot, all right, have a little detector here. Okay, that's Rob's eye, since he likes looking at laser light. Okay, so you have your light source, in this case, my light source is continuous or discontinuous? Continuous. If it's discontinuous, there may not even be a need for a monochromator, right? However, if you look at like the discharge lamps, if you want one particular wavelength, you're still going to need a monochromator because it's kicking off more than one wavelength, even though it's discontinuous. So you still pretty much need a monochromator. And you saw that in the AA, and we'll get into that in much more detail later. But all the light travels into the monochromator, right? All of the different colors. And then what does the grading do? Well, it rotates. Let's say, what color do you want out of the monochromator? You want to select pink? I don't know. I don't have a pink, but I have that orange.
In between.
Right? So you get it'll bounce up here. Now the mirror is, the mirror's fixed. Right? So whatever strikes it, right? Yeah, let's see. Let's do red because my ink is red here. All right, so the red's going up here. Right? So all the other wavelengths are hitting down here or up here, right? Okay. If they even make it that far because we're cranked over so far. But that's pretty much the idea how a monochromator works. Right? Who's used the AA? Okay. Anna. Do you remember adjusting something called blank width? What's it called? Slit width, right? What does slit width have to do with monochromator? Yeah, the width of these slits. This guy. Slit widths. Those are your slit widths. Okay. So if you make that slit width wider, more light. Yeah. Now it's not going to be as good, and it won't be such a narrow wavelength, but you get more light. Okay. Slit width. Okay.
Everything in that box is considered a monochromator?
Yeah, just that part's a monochromator, right? So yeah, the detector and the light source are outside of it. Yeah, you have the grating and the mirror and the slit widths, and there might be more. I'm sure there's more mirrors and stuff in there than what I've got. This is just the basic general idea. Okay. The most common detector, photomultiplier tube. Okay. Where is it?
The most common?
Yeah. Most common detector I have laying around here somewhere because I have a broken one. Here it is. Okay, can you see it? So it's got this is the part, that's after the, what is it called? It's going to be immediately after in our little flow diagram of the parts of the instrument. It's going to be right after the sample, right? Whatever light gets through the sample. So that see that little silver kind of surface? Okay, so that's the light's going to be striking it. Blank effect, Adriana, where light strikes a metal and an electron gets kicked out. Photoelectric effect. Right? Photoelectric effect. That's what this is. So you have some emissive material there that's really easy to kick out electrons. Really easy. So light strikes it. Doesn't matter what the wavelength is, because its threshold is really, really low. Right? Light strikes it, kicks out an electron or two. Okay? So if you flip this around to the side and see where those electrons are going. You notice, so look at all these wires on the bottom. Each one is connected to a piece of copper, and it's kind of shaped like a cup. And we need to start drawing it now, because now we're looking at the inside guts. So first, let's get that top part where you had this.
That's the shiny thing.
Yeah, the shiny thing. But we need to call it a photo-emissive material or something. Right? Okay. And so then you have these copper shaped. Let's make him positive, I don't know, 100 volts or something. So electrons have what charge? Negative. So those few electrons that got kicked out, all right? So first, what's the symbol for a photon of light? HV, or H nu, right? All right, photon light's coming in, gets kicked into an electron. Maybe you get two of them, I don't know, not very many, right? But they strike our 100-volt little piece of copper, and that little piece of copper guy, he's covered with more of that photoemissive material. Right? So when an electron kicks it, more electrons will get knocked out of there. but let's have this guy at, I don't know, 200 volts. So now you get the electrons that are kicked out of there. What? Now you get a bunch more going to this guy, the next positive voltage. Remember, and again, he's coated with that photoemissive material. See how this just keeps going, right? And then you have another one. Yeah, it just needs to be a higher voltage. They keep stepping it up. I'm just making up numbers, right? Just make it higher and higher and higher, and you just end up getting more and more electrons. All right? More and more electrons coming down. Cascading down is really the word. We're generating a cascade of electrons. That's what they... All right? So that just keeps going. Now, you see in the photomultiplier tube, there's a lot of those silver cups. Now, we're not supposed to call them silver cups. We're supposed to call them, I don't know if this was in the reading or not. They're called dinodes.
Oh, yeah.
Was it in the reading?
Yeah.
You say so, probably.
Was it wrong? That'd be like a 90%.
All right. Okay, so draw. So keep drawing this, right? In your draw a couple more of these, right, to illustrate this. Right? Draw a couple more to show that the electrons are just piling down there. Then at the very bottom, okay, at the very bottom, whatever you draw, I don't know, draw some kind of anode. Oh, that'd be anode. Sorry, not cathode. It'd be anode.
Yeah.
All right. And then we'll get our signal. We'll get our current.
The electrons bounce into the anode?
Yeah, that's where this whole cascade, this whole shower of electrons are going to end up. So from one little photon of light, you get this nice, big, strong signal. Okay. So it's really sensitive, but it's got a problem. It's got a real problem. Right now, this guy, right, if we hooked him up and put him in the machine, right, and we totally closed up the sample holder, made everything completely dark, there's still a signal. And the UV vis, there's still a signal, even though everything's off. You know, there's no light striking anything. And they call that dark current. So dark current is your background signal. This photoemissive material at room temperature, electrons get kicked out of there, just because room temperature is hot. For this, it's objective. So this is hot, so it kicks out electrons, and it just needs to emit a few, and you get that cascade of electrons. You get this current, but there's no sample there, so they call it dark current. It's a bad thing. You want to get rid of it, right? Dark current, bad. So
What is dark current when using DMT? Bad.
So what is it? How would you explain what dark current is?
Current that you can't see.
How would you explain it? It's the signal, right, from the photomultiplier tube, or a current generated by a photomultiplier tube, even though there's no light, right? Even though there's no light. So it's not a good thing. It's coming from the photoemissive material. It just, remember, this is a positive voltage. It just sucks them right out of there. It's so easy, because it needs to be easy, because you want them to kick out electrons for this broad range of wavelengths. So it's pretty easy to kick out electrons there. So how do you minimize dark current? Now here's a hint over here. This is the electrons from that photoemissive material, right? And it's like a photographic film. And they applied a voltage across that photoemissive material, and these are electrons that were pulled out, that struck the material. You can see little dots. Okay, so the C probably stands for Celsius. So how could you minimize dark current? Decreasing the temperature, make it cold. And we could have done that if we spent another $30,000 on our UV vis. We would have to continually pour in liquid nitrogen to cool our PMT. But what's the point? Right, it works fine. But see how ice bath wouldn't work? It needs to get really cold. Otherwise, it doesn't have much effect. All right. Hey, here's a question for you. How many? Let's see. What percent? If you said blank in 10 in Minnesota have a gun or a hunting license, that's hunting license. Blank in 10.
Yeah.
Blank in 10 have a hunting license in Minnesota. What would you say? It's 1.
Yeah, I believe it.
That's still pretty high. 1 in 10 have a hunting license.
Not everybody from Minnesota's right. Remember, it's only 6.
I thought that was high. Okay, so that's it.